Hello everyone. Welcome to Mr. Shin's Steel Academy. I am Mr. Shin, possessing 35 years of field experience at Hyundai Steel. Hyundai Steel's Louisiana plant opening in 2029. I launched this channel to share core steelmaking knowledge with the world. Hot metal molten iron refers to liquid iron made by melting iron, or pig iron is iron produced by pouring liquid molten iron into a mold called a pig casting machine. Let's look at pig iron figure 1. There are pig irons about the size of a palm, and some are 2 to 3 times larger. In the past, in the 19th century, before pig casting machines were introduced, multiple pig-shaped trenches were dug in the ground. Molten iron was flowed into a central trench connected to the pig trenches to make pig iron. Since its shape resembled a mother pig nursing her piglets, it is called pig iron. Cast iron is iron produced by melting pig iron as a raw material. In other words, it is iron made by melting pig iron. Common examples around us include cast iron cauldrons and pots. Steel melts at 1535 degrees Celsius, while cast iron melts at a lower 1350 degrees Celsius. Cast iron is iron produced by melting pig iron as a raw material. Cast iron is more brittle and has lower thermal conductivity than steel. Why do we grill pork belly with thermal conductivity about 1.5 times lower than steel? The meat cooks gently without burning, making it even tastier. However, due to high brittleness, the pot can crack if dropped. So far, we have looked at the terms molten iron, pig iron, and cast iron. These are irons with high carbon content exceeding 2%. Molten steel is liquid iron manufactured with a low carbon content of 2% or less. Let's learn about the steel manufacturing methods. The blast furnace method is a manufacturing process that melts iron or to make molten iron. Figure 2 shows a blast furnace plant. Due to its characteristics, most blast furnace facilities are very high, exceeding 100 meters. Main materials like iron, ore, and auxiliary materials like coke and lime move to the top. Once charged through the top hopper, thermodynamic and chemical reactions occur in each temperature zone inside. As a result, liquid hot metal at about 1500 degrees Celsius is produced. The process of producing hot metal through a blast furnace is called the iron-making process. From today, we will learn about the steel-making process that produces molten steel with a carbon content of 2% or less. The converter method produces molten steel using molten iron from blast furnaces and scrap with a ratio of about 8 to 2. When charging raw materials into the converter, hot metal and scrap are charged in order. The converter body tilts forward to facilitate charging. This prevents hot metal from splashing out and causing accidents. Conversely, when tapping molten steel, the converter tilts in the opposite direction to pour it into a ladle. That is why the Korean word for converter, Jon-ro, in Korean, uses the character Jon, meaning to rotate. Since hot metal from the blast furnace has high carbon, oxygen is injected in the converter to burn it off. This is called decarburization. That's why the converter is also called BOF, basic oxygen furnace. This corresponds to the primary refining process. Afterwards, through secondary refining, RH/VD, continuous casting and rolling, high-quality automotive steel sheets are produced. Hyundai Steel's future plant in Louisiana, USA, plans to produce automotive steel using the electric arc furnace method to reduce carbon emissions. Are produced. The blast furnace method uses iron ore to produce high-quality virgin iron that is almost free of impurities like Cu, Sn, Ni, and nitrogen. Why it is capable of producing automotive steel sheets for exterior panels. However, Hyundai Steel announced that its future plant in Louisiana has chosen the electric arc furnace method, not the blast furnace, to reduce carbon emissions. that they would produce automotive steel sheets using this method. Then, with what EF operation method can we secure automotive steel quality comparable to the virgin iron of a blast furnace? Also, why Louisiana? This region has abundant reserves of natural gas, LNG. By using this natural gas to remove oxygen from iron, or at high temperatures, we can obtain DRI, direct reduced iron. DRI has a much higher pure Fe content, 84-94%, than iron ore and almost no impurities, making it a raw material that substitutes for virgin iron. Therefore, using DRI as the main raw material in the EAF method enables the commercial production of automotive steel sheets that substitutes for virgin iron. DRI reacts easily with oxygen in the air. The oxidation heat generated causes a very high risk of fire. Steel sheets that substitutes for virgin iron. To prevent such fires, nitrogen purging is legally mandatory during DRI storage, transport, and use. HBI hot briquette iron is made by compressing hot DRI under high pressure into a shape like a foldable phone. DRI is classified into hot DRI and cold DRI depending on the temperature. The Louisiana plant is expected to use high-quality scrap and simultaneously employ a method of charging hot DRI directly into the electric furnace. EF melts scrap, DRI, and pig iron to make steel. This is a charging bucket used to load scrap. Scrap is charged from the bucket into the furnace. Melting scrap with electricity is the steel-making process. The operation sequence is charging, power on, melting, refining, tapping. For melting, power is applied to graphite electrodes to melt the scrap. If there are 3 electrodes, it is called an AC electric furnace. This image shows an AC EAF. A furnace with 1 electrode is a DC electric furnace. In DC EAF, the top electrode is the negative minus symbol cathode, and the bottom anode is the positive plus symbol anode, which absorbs the arc. High current creates an ultra-hot spark at the electrode tip. This spark, over 3000 degrees Celsius, is called an arc. Traditional DC furnaces used 1 electrode, 150-ton class. Recent 400-ton furnaces are evolving into twin cathode types. Tokyo Steel's Tahara plant operates this twin electrode type. POSCO Gwangyang plant will also adopt this type in 2026. June. Hyundai Steel Louisiana will likely use a similar DC EAF. DC offers superior stirring, ensuring uniform steel quality. Easy impurity removal makes it ideal for automotive steel. A large-scale DC EAF is essential for an annual production of 2.7 million tons. So far, we covered iron making, steel making, and the DC EAF method that replaces blast furnace virgin iron. Now, we are entering a crucial phase to truly understand the EAF process. But everyone, please don't worry. With my decades of practical field experience, I will explain it in the easiest way possible. Let's look at what an arc is and how it is generated. Even with power on, electricity doesn't flow because air is an insulator. However, applying very high voltage forces current to flow through the air. This creates intense heat over 3,000 degrees Celsius and white light. This phenomenon occurring in the air is called arc discharge. If scrap is between the electrodes, it acts as a medium and melts. ACEFs generate arcs by alternating polarity between 2 of the 3 electrodes. It switches 60 times per second, 60 Hz, creating powerful arcs. The sequence flows A plus B, B plus C, C plus A. At any moment, one phase has no arc, while the other 2 generate the arc with plus or minus polarity. The resulting arc column bends into a curved shape due to the magnetic field. In the ACEAF, arcs actually occur in only 2 phases at a time, while one phase is interrupted. However, alternating at 60 Hz, it looks like continuous arcs. from all three electrodes when viewed through cobalt glasses. In contrast, DCEFs use a rectifier, so there is no arc interruption. This will be explained in detail in the future EF equipment lesson. This causes an outward arc bending of about 10 to 30 degrees. Therefore, due to Lorenz's law, the molten steel in an AC EAF dot normally rotates in a counterclockwise direction. If you open the slag door and look inside wearing cobalt safety glasses, you can actually observe the slag layer rotating counterclockwise. However, since the polarity changes every 1/60th of a second, we will wrap up the AC theory here and cover it in detail in the future EAF equipment lesson. In DCEF, the bottom anode plus absorbs the arc from the top graphite cathode. The scrap positioned in between is melted by the heat of this arc. Large DCEFs with two top electrodes have bottom electrodes aligned 1:1 symmetrically multi-rod type. Scrap melting speeds are expected to be faster when using two arcs compared to a single electrode. Also, the molten steel stirring force surging from the bottom to the top is expected to be excellent. This effectively releases impurity gases, hydrogen, oxygen, nitrogen, into the air. Naturally, this results in superior steel cleanliness. In Lesson 01, we learned about the principles of how scrap is melted in the EF method. Lesson 02, Understanding EF Process. This figure shows the progression sequence of the electric furnace melting period. The melting period is the initial process of the electric furnace where scrap is melted by the arc heat of the electrodes to create molten steel. From the beginning of the melting period, oxygen is injected from the shell burner to shorten the melting time. As we move from left A to right C, the electrodes tunnel through and melt the scrap using arc heat. Is melted as shown in D. Eventually, it reaches the point where most of the scrap is melted as shown in D. Supplying electricity to electrodes is called power on. Arc length increases with higher voltage, and arc thickness increases with higher current. Figure A is the initial power on stage called the ignition period, where low voltage is used to prevent damage to the furnace roof from the arc. Figure B shows the progress after some time, called the boring period because it resembles drilling a hole. At this stage, high voltage is used to increase the boring speed to the furnace bottom, which is referred to as long arc operation. Figure C is the late melting stage where molten steel forms with slag on top. Slag is the residue from flux, byproducts and impurities within the scrap. Carbon agents like graphite or coke dust must be injected into the slag layer to create foaming slag, burying the electrode arc within it. Injection means projecting materials into the slag layer at high pressure through a pipe. Decades ago, operators carried lance pipes on their shoulders to manually inject graphite and oxygen directly into the molten steel. Today, this process is robotized with water-cooled manipulators, allowing operators to safely control injection remotely from the control room. This image shows the operation floor of a 50-ton EF. The circled part is the water-cooled lance manipulator, currently in its home position. Continuous air injection from the nozzle during movement, and operation prevents clogging caused by slag. Key point: from the start of meltdown, oxygen and graphite carbon are injected together to create foaming slag. A breakdown of this device creates an emergency. It is a vital, lifeline-like equipment for melting up. From melting stages A to D, the injection rates of oxygen and LNG gas are automatically adjusted and continuously supplied. At the final melting stage, D, when more than 70% of the scrap is melted, it is called meltdown. This marks the completion of the melting period. In Lesson 03, we will cover the core areas of EF. operation, the importance of foaming slag after, meltdown, oxidation, refining, and tapping. Today's first lesson ran a bit long at about 17 minutes. This lecture series will continue even after the Louisiana Hyundai steel plant begins operations. Your likes, subscriptions, and notifications are a huge support for preparing these lectures. Thank you and see you in the next lesson.